All right, so for the final stretch today, we'll continue to talk about addresses, and then we will finish off by a pretty long example to illustrate how these addresses are interrelated and how we can actually transfer information over an internet. So we stop by talking about the three different types of addresses: the internet name, the IP addresses, and the link layer addresses, and how to translate those between these using DNS and ARP. So just to make a small check here. So for instance, which of the following is a network address? There's an IP, a MAC, port number, and www.chalmers.se. So which one of those would be a network address? I'll give you a few seconds to think about that. So how many for the IP address? Okay. MAC address, port number, and internet name, www. Okay. So here the correct answer is the most correct answer is the IP address. Okay, so that's your main network address. Now, the internet name is somehow synonymous with the IP address, but for the purpose of the network layer, it only understands IP addresses, not internet names. Okay. Now, to the next question is, which of the following is then a link layer address? So IP address is no one, I guess. MAC address, port number, www.chalmers.se. No. Okay, so the correct answer here is the MAC address. Okay, so that's this is a particular technology link layer address. So for another technology, which is not Ethernet, you have another addressing scheme. But for the main running example through the course will be Ethernet. But please be aware of that there are, of course, other network technologies here. Now, so this issue about the port number here, that is something that addresses a particular application layer protocol, right? So it's an application layer address. What makes this a little bit confusing is that sometimes one talks about hardware ports, okay? And these are network interface cards, right? So the name port could be different things, mean different things in different contexts. But port number 80, for instance, is the service access point that HTTP listens to at the web server side. Okay. All right. Now, if we continue here, yeah. So these network interface cards, for instance, how do we know which ones we have? Okay, so there is this little utility called network setup on a Mac. So here are the ones which are available on my laptop. Okay, so here we see it says hardware port. Okay, so it has no port number, but it has a MAC address associated with it. So it's a network interface card. It's a USB, and this is some USB port with a few other things, and it's called EN6. So that's just the name of that network interface card, almost like you have an internet name to map to an IP address. You have also a shorthand notation for the interface card, which has this MAC address. Okay. And then there is a Wi-Fi, there is a Bluetooth, there's a Thunderbolt 1 and Thunderbolt 2, and then a Thunderbolt bridge here. All of them have different MAC addresses. Okay. So in this particular computer, there's a bunch of different network interface cards, All of them could have assigned IP addresses or perhaps not be active and don't have an IP address. These numbers will never change. So when I do this command at home, I will get the same information, right? For these things. Okay, we continue. So let's go into an example here to show how all of these things are interrelated. So here we have a simple network. We have Alice, who's attached by a cable to her switch, like this. Okay. So this is the local area network, and then suppose this is Alice's computer, this is Alice's host, right? This is Alice local area network. Now, from this switch, there is a connection to a router called R1, and R1 is connected to another router called R2 over a wide area network. And then at R2 is connected then to Bob's switch, and Bob is attached to that switch. Okay, so that's the actual very simple network. Now, for everything to start, we know that all the physical devices here have their MAC addresses. They get that when they are born, when they are manufactured. Okay, but then the first thing that needs for this to work is that we need to assign network addresses to these, i.e. IP addresses. And this could be done through manual configuration or the use of this dynamic host configuration protocol, DHCP. Okay, so suppose that this has happened now. Okay, so now we have these IP addresses. Okay, what IP addresses how do I know what IP addresses I'm assigned to? Well, I can check that by doing another command, nets.rn, I think. Okay, so here we got a bunch of things here. Let's wait with this actually. Okay. So first of all, then I get these network addresses. So this is the IP address that Alice has gotten, NA. N1 here is an IP address for the router which has 3 interface cards, one here, and one here. All of them have different IP addresses, right? And different MAC addresses also, but different IP addresses in here. Router number 2 has also 3 IP addresses, one for this network interface card, one for this one, and one for this one. And Bob has NB. Okay. Now, suppose that Alice would like to send some packet to Bob. Okay. Then there is some data that Alice would like to send. And then this is encapsulated then in an IP packet which contains the addresses. Okay. And the addressing scheme, it comes from, it should go to Bob's IP address, and it should come from Alice. Okay, so this together forms the IP packet. Okay. So there is some data that needs to be transmitted, the blue parts, and it needs to go to Bob. Okay, so somehow Alice has figured out the IP address of Bob, okay, through DNS or whatever. And then Alice, of course, knows its own IP address because Alice got that through DHCP or something like this. Okay. So now this packet needs to go over this, needs to find its way through the network to get to Bob. How's that going to be done? Well, at the highest layer, at the network layer, we have each of the communicating parties here, the host and the router has a what's known as a forwarding table or routing table. So this is a forwarding table, also known as a routing table. Okay. This is something which is dynamically created and dynamically updated all the time to react to network changes. And the exact how this looks in practice is a little bit more complicated than the table I look here. But there are three components that needs to be there: a destination IP address, the next hop IP address, and something that identifies which interface where we can find the next hop IP. Okay, so we know. Okay, so let's go one more step here. So in the router there is also an IP address, one of these tables, and then there is one in the router here too. Okay, so let's see how these together collectively form the network path. Okay, so at the beginning, Alice IP layer gets this data from above with two network addresses. And Alice then needs to figure out, the IP layer in Alice computer need to figure out what to do with this IP packet. Okay, it should go to Bob, right? So it knows it needs to go to Bob, and then it looks in the destination column, to figure out where Bob's address is. Okay, it's here. Then it knows, the IP layer knows that, okay, if it's going to Bob, the next hop it should go to is N1. Okay, whatever router that has IP address N1 is the next destination, and that IP address N1 can be found on my local interface, which has IP address NA. So this identifies the local interface. Now Alice only has one IP address, so it's the same here. But as you see in the router, it has several interfaces, so it had several possibilities here. Okay, so basically now the IP layer at Alice knows, okay, I need to go to N1 and I find this at interface NA. And then the data then goes this way. It goes out this link, and then it's picked up by router number 1. Router number 1 then looks at the data it just got and say, okay, it comes from NA and it should go to NB. It then inspects NB here and see, okay, NB. Then it needs to go to N3, and I find that on my local interface called N2. So N2 here. Right? So it knows then, okay, I should transmit this packet out of this link, over this link, because it says N2 here, and it should be addressed then to N3. And then it goes over this link, and then when it comes to router number 2 looks at this. Okay, it should go to NB, and it should go. Where should it go then? Well, NB. Okay, next hop IP is actually NB, and it should go over the interface, the local interface, which is called N4. And then it's moving across this until it's picked up by Bob. Okay, so the collective 3 tables then defines a network path through the network, but one single table does not tell the entire path, only the next hop. Okay, and the reason for this, if you think about it, is fairly obvious. If this laptop should contain the complete path to all possible nodes on the internet, that table is quite big, right? It will not fit in the memory of this computer. Okay, so the only thing which is stored here is where it should go next. What is the next router it should go to? Okay, which means that basically many IP addresses, destination addresses, goes through the same router. As a matter of fact, a host like this typically feeds all its packets through the default router, and then the default router sends out, maybe splits this later on, right? It's almost like a mail company that gets an address, and if the post office here in Gothenburg gets something that says, you know, it should go to Bob, who lives at this and this road in Stockholm, right? It will only look at this and say, okay, it needs to go to Stockholm, and then toss it into the Stockholm bin, right? And then it goes to Stockholm. When it comes to Stockholm, it says, oh, it needs to go to this post number address, so it goes to that district in Stockholm, and it put in that bin, and then fed out to this. And then it goes to the local office, okay, it actually needs to go to this particular address, this street name, it goes to the street name, and when it arrives in the mailbox, you know, the people that live at that address says, okay, it needs to go to Bob, Caesar, or David, right? So it's a hierarchical address, and the reason why it's hierarchical is because you don't have to make a full decision at each point when you route it, and that's to keep the routing table small. Okay? All right, so terminology here, so let me do this and then do this. Oops. Sorry, it became messy here. So terminology. I don't know how to get rid of this. Can I do this? No. Done. This is amazingly stupid. Okay. Anyways, forwarding, that's the process of moving a packet over one node. So moving the packet from here to here called forwarding, and that's done by querying the forwarding table. The forwarding table defines a path, a route through the network, and these are dynamically updated to reflect changes in the network. The process of populating a forwarding table is called routing. Okay. So if one should be precise, forwarding is moving a packet to the right destination. Routing is to figure out what should be in the forwarding table. Most often, and I will do this also, we talk about routing in the general sense. We actually might mean forwarding or routing. So sometimes we make mistakes. So sometimes this is also called a routing table. Okay, right. So let's continue. Address resolution protocol. Here, to actually transmit this IP packet over a link, over a network, the IP address is not useful for this. It needs to be translated into the corresponding link layer address. Okay, so here we have 4 systems. It could be a host or a router. We don't care really. Has 4 systems with network addresses and link addresses. This is the say the IP layer, and this is the Ethernet layer. Say Ethernet. And all of these nodes are then somehow attached to the same local area network here. Right? If system number 1 wants to transmit an IP packet to system number 2, the IP entity in system number 1 needs to translate this IP address to something that the link layer understands. Okay, and the link layer in system 1 only understands link layer addresses. It doesn't understand IP addresses. So the IP layer here needs to translate the IP address, destination IP address, to the corresponding link layer address. Okay, so if the destination is N2, so this is the destination, we know that N2 is where it's supposed to go to, but IP here needs to tell its link layer where to send the packet, and it should send it to a packet to a host which has link layer address L2. So N1 and L1 are pointing at the same network card. N2 and L2 are pointing to the same network card. N3 and L3 to the same, and so forth, right? But the IP layer here does not know about the link layer addresses here. Therefore, it needs to figure this one out before it can even transmit anything. So how that works is that one uses ARP, and ARP in system 1 broadcasts a ARP request. And it's basically like, what is the link layer address of the node with IP address N2? Okay, and note here that it broadcasts this address. So essentially what the IP layer at system 1 is, it tells the Ethernet layer here, send a message using the broadcast link address. Okay, and then that broadcast link address contains then the message contains an ARP request like this. Okay, the ARP request is then processed by all of the attached systems, and then the system with the requested IP address replies with an ARP response saying, and here is unicast to system A, system 1. The node with IP N2 has link layer address L2. Okay, so in pictures, what happens now is that IP layer in system 1 needs to translate N2 to L2, and it does that by sending out a request. And it's broadcasted, so it's picked up by all network layers, by all link layer link layers here, and it's a valid address, so it's pushed up to the layer above it, where ARP is processing this request. ARP in system 2 says, okay, well, I'm actually the system that has IP address N2, so I should respond to this. The ARP in system 3 says, oh, I'm not the system that has link network address N2, so I won't do anything with it. I will toss this request away, right? So then only system 2 answers. Okay, so here's the answer, and it's addressed only to this system. So it uses link layer address L1. Now, this data, of course, goes out also over this cable, and it's picked up by the link layers here. But these link layers looks at the link layer address and say, okay, it's not to me, so I toss it away. Okay, so unicast means that only one of these link layers will actually send up the data to its corresponding upper layer. If it's broadcast, it means that all network layers, all link layer layers will pass up the information to the corresponding protocol. So note here that the packet never goes to ARP in this case, right? It's blocked already here. Okay, questions so far? No. Okay, so let's see how this works then. Again, what do we want to do? Well, we have some data from Alice that needs to reach Bob. Okay, so the first thing to happen is that we need to have network addresses, and we also know that all of the interfaces here already have link layer addresses. So in Alice has a network interface card with an IP address and a MAC address, NA and L1 respectively. Okay. So the first thing that happens when we have a packet that should go from Alice to Bob is the following. If we look in Alice node here, there is a a network layer, a data link layer, and a physical layer. Okay, there is transport layer and other things also, but we just narrow down it now from the network layer and below. So we have a network layer, data link layer, physical layer. The data link layer has an address, LA. The network layer has an address, NA. So this is an IP address, and this is an Ethernet MAC address. Okay. There is also a forwarding table that resides in the network layer to define the network path, right? So what happens now? First of all, there is some data coming from the transport layer down to the network layer together with a destination address. So this data should go to the node with IP address NB, which is Bob, right? Because we have NB here. Okay, so the network layer then looks at this and say, okay, NB, I wonder what link address that is. NB, where should it go? And then look in the forwarding table and then say, okay, it needs to go to N1. Okay, good. So now I know that this packet, the first hop is to N1, but what is the link layer address for L1? Well, then I use ARP to figure this one out. So ARP at Alice node sends out an ARP request and asks, okay, which node has IP address N1? And then router number 1 says, it's me. I have link layer address L1, and this then goes out here. And now the network layer has everything it needs in order to ask its data link layer to transmit the information. It has the link layer address. Okay, so it pushes down the data, okay, plus the control information from the network layer, which is the, among other things, the network, source address and the destination address, and then together with the link layer address. Okay, the data link layer here looks at this as payload, so it does nothing with it, doesn't expect it, doesn't look into it. This is only the payload it needs to transmit, and it needs to transmit that to the node which has link layer address L1. And then this is then pushed down to the physical layer, and the physical layer gets the data, the IP addresses, and the link layer addresses. Okay. For the physical layer here, it doesn't look at this. It just converts this to a signal like this and pushes it out on whatever cable it's attached to. Right? It just goes out here. Okay, so that was the first step. So now we know that there is a signal being pushed out on this link here, namely this signal. So what happens then in R1? Okay, so before we go there, the order of destination and source. So here's source and destination. Here it's destination and source. So it's reversed, these two orders. And this is, I guess, for historical reasons why it's like that. So it's not a typo here. It's actually how it is. You know, it doesn't matter, of course, in which order they are, as long as you can distinguish between them, right? Okay, now in R1 here, what happens then? Well, the first thing that happens is that there is some information coming on there is a signal here coming from Alice, which is picked up by the physical layer in R1. Or actually, it comes this way, right? So it's picked up here, and then it's pushed up to the data link layer. So the data link layer here at the network interface card here gets this information. It decapsulates this, and then it arrives to the network layer. Okay. So now the network layer here has an IP packet. It comes from Alice. It should go to Bob. So what should the router do with this? Well, it should push it out into some direction, right, to some other router or host. So how do we know which one to do? Well, we look in the forwarding table. So the destination is NB. We look in the forwarding table here. Okay, and the forwarding table says, okay, it needs to go to N3. It needs to go here, right? Okay, good, but what link layer address should I use? Wonders IP here. Well, it uses then ARP and sends out an ARP request and asking, okay, which node has N3 as IP address? Router 2 has this and answers, okay, I have that and my link layer address is L3. L3 then goes over here, and now we can be pushed down to the data link layer here. Okay, now this data link layer has link layer L2, so it is the thing that's here. This link layer has link layer address L1, which is the link layer which is here. Okay, two different link layers, but the same network layer. Okay, so the network layer serves many link layers, or has many link layers to its disposals, one per outgoing link. Okay. Now, so continuing here, this data is then pushed down from the network layer into the appropriate link layer with the appropriate link layer address, where it should go next. And then it goes down to the physical layer, and then it's sent out to R2, or it's sent out on this link essentially. Questions? Confusing or crystal clear? I interpret that as pretty clear. Okay. All right. So this is the router. This is what routers do, right? They look at IP packets and forward them down the right way. That's what they do. Okay. Now, another packet that comes in here, maybe that should go out into this link instead, but that's defined by the forwarding table here. Okay. Good. So what happens then next? In R2, exactly the same process changes. So what's in red is what's different here. And obviously what is different is the incoming packet's link layer addresses, because the link layer address at the receiving network interface card is different. And then what is different is where the next hop IP address should be, which is actually the destination. And that has a particular link layer address, of course. So that should be then pushed down through the network interface card, which is here, which has that's a typo. It should be this one should be L4. Sorry for that. Right? It's L4 here, and it should go to LB. So LB is correct here. Okay. So, and this is correct. It goes from L4 to LB, and then it goes out here. So the same thing happens here, and then at the receiving end, basically data comes here, goes up here, and then the network layer sees, it's for me, and then it feeds up the data to the layer above it. Questions? Okay. So hopefully now it's fairly clear that we need both network layer addresses and link layer addresses because they serve different purposes. The network layer, the IP address, is used to figure out the route over the network. The link layer addresses is needed to transfer information over one network. We have the IP layer on top. It understands IP addresses. The link layer below does not understand IP addresses. It understands link layer addresses. The network layer in order to use the link layer, needs to feed a link layer address down. Right? So it's up to the IP layer to figure out what link layer address to use, and it uses ARP to do this. It's a helper protocol. Okay. Question? Yes.
Is the link layer having a tail layer?
Oh, so does the link layer add a tail? Typically, yes. So it didn't really fit on the slide here, but at the end here, let's do this in the right, sort of the right color. There will be like a trailer like this. And we will see later on what is contained in the trailer, but I can give you a little bit of a preview here. I mean, these addresses are obviously needed for the receiving network layer, link layer to know if it's for them or not. The trailer here is used for error control, right? So whether to figure out whether these bits are the correct ones, because whenever there is a transfer over a physical link, there is always a chance for an error, a risk for an error. Yes?
I just need to clarify the headers for the link layer
Mm.
is from the router that sends, or the thing that sends it to the other, whereas the network layer has the original source to the.
Yeah. So if we look at this, for instance, this might be illustrating your question. So the question is, we see here as we go, as the packet is transferred from Alice to Bob, it never changes, right? It's actually the same. It has the destination and the source, always. So what is changing is the link layer addresses as we go from one network to the other. So did that answer your question?
Yeah, I think so, but in that slide,
Yeah?
there might be a typo, I think.
Possibly, right.
It's, when it goes from L3.
Okay, so here it should go to, first of all, it needs to go to R2, so it should go to L3, which is correct, but it should not be LA here. This should be L2. Okay. Sorry for that. I'll correct it and put out the right slides. Yeah. So, and that's important. I mean, from the network layer perspective, the packet never changes. It just goes over the networks. But for each link, the encapsulating data link frame, these addresses change as we go over. And the link layer never looks at the content here. It never uses these addresses to do any of its job, right? It only uses, so that's important also. So this is the only information that data link layer looks at, never at these, okay? Okay. So, actually that's everything I had for today. So we will meet again tomorrow at 3 o'clock, and then we will start to talk about the beautiful physical layer. That's my favorite, actually. That's my background is it. So let's do that for a couple of lectures, and then you should be ready to start your projects by mid next week, I would say. Okay, so see you tomorrow.